From the moment we open our eyes, we are bathed in light. It illuminates our world, revealing a tapestry of colors, shapes, and movements. But what exactly is this ethereal phenomenon that allows us to perceive the universe around us? This fundamental question has captivated scientists and philosophers for centuries, leading to a profound exploration of light's true nature. The ancient Greeks pondered the nature of light, with some believing it to be composed of tiny particles emitted from our eyes. Others, like the philosopher Empedocles, proposed that light traveled as waves, similar to the ripples on the surface of a pond. However, it wasn't until the scientific revolution that a more rigorous investigation into the properties of light began. The stage was set for a scientific duel, a clash of titans that would forever change our understanding of the cosmos. Two competing theories emerged, each seeking to explain the mysteries of light: the wave theory and the particle theory. Like two sides of a cosmic coin, these theories would shape our scientific understanding, leading us on a journey of discovery and wonder. In the late 17th century, Dutch scientist Christian Huygens put forth a compelling argument for the wave-like nature of light. Huygens proposed that light travels outward from a source in a series of expanding spheres, much like ripples spreading from a stone thrown into a pond. This became known as Huygens's principle. Huygens's wave theory elegantly explained several observed properties of light, such as reflection and refraction. Reflection, the bouncing of light off a surface, could be understood as waves bouncing off a barrier. Refraction, the bending of light as it passes from one medium to another, could be explained by the change in speed of the light waves. However, Huygens's theory faced a significant challenge. It couldn't explain the phenomenon of diffraction. Diffraction refers to the bending of light waves around obstacles, causing them to spread out. It was not until the early 19th century that a crucial experiment would solidify the wave theory's place in the scientific landscape. Sir Isaac Newton, a towering figure of the scientific revolution, proposed an alternative theory of light. Newton believed that light was composed of tiny, weightless particles that he called corpuscles. According to his corpuscular theory, these particles traveled in straight lines and interacted with matter like tiny billiard balls. Newton's theory could readily explain reflection and refraction. Reflection was simply the bouncing of corpuscles off a surface, while refraction was explained by the change in speed and direction of the corpuscles as they passed from one medium to another. Furthermore, Newton's reputation and the elegance of his theory led to its widespread acceptance for over a century. The wave theory, lacking a definitive explanation for diffraction, remained overshadowed. However, the tide was about to turn, ushering in a new era of understanding about the nature of light. Section 4. Einstein, Planck, and the Quantum Revolution. As the 19th century ended, cracks appeared in classical physics. Phenomena like blackbody radiation and the photoelectric effect challenged the wave theory of light. In 1900, Max Planck proposed quantum theory to explain blackbody radiation. Planck suggested energy is emitted in discrete packets called quanta. This idea challenged the classical view of energy as a continuous wave. In 1905, Einstein explained the photoelectric effect using Planck's quantum theory. Light shining on a metal surface causes electron emission, unexplained by wave theory. Einstein proposed light exists as discrete packets called photons. These discoveries shattered classical physics, revealing a stranger universe. Light was not simply a wave or a particle, but more enigmatic. Section 5. Wave-particle duality, light's strange secret. The early 20th century witnessed a paradigm shift in our understanding of light. It became increasingly clear that light exhibited a bewildering dual nature, behaving as both a wave and a particle depending on the experiment and the way it was observed. This wave-particle duality, as it came to be known, challenged the very foundations of classical physics. In 1924, Louis de Broglie proposed a revolutionary idea. If light, a wave, could also behave like a particle, then perhaps particles like electrons could also exhibit wave-like properties. This radical notion, known as de Broglie's hypothesis, was experimentally confirmed a few years later, further blurring the lines between the macroscopic world of our everyday experience and the bizarre, counterintuitive realm of quantum mechanics. The wave-particle duality of light presented a profound challenge to our classical intuitions. How could something be both a wave, spread out over space, and a particle, localized at a single point? This seemingly paradoxical nature of light forced physicists to rethink their fundamental understanding of the universe. Section 6. Quantum Mechanics, Embracing the Paradox. The wave-particle duality of light, along with other perplexing phenomena observed at the atomic and subatomic levels, led to the development of quantum mechanics, a revolutionary new framework for understanding the universe. Quantum mechanics embraced the inherent uncertainty and probabilistic nature of the microscopic world, abandoning the deterministic worldview of classical physics. In the quantum realm, particles like photons and electrons do not follow well-defined trajectories, but rather exist as probability waves, spread out over space. The act of observation, of interacting with these quantum entities, causes their wave function to collapse, forcing them into a definite state. This inherent randomness and uncertainty at the heart of quantum mechanics challenged our classical intuitions about causality and determinism. Yet, despite its strangeness, quantum mechanics has proven to be an incredibly successful theory, accurately predicting a wide range of phenomena from the behavior of atoms to the properties of materials. Section 7. The Universe of Light, a Final Reflection. Our journey through the history of light has taken us from the ancient Greek philosophers to the cutting edge of modern physics. We have witnessed the clash of titans and the birth of a revolutionary new framework for understanding the universe. Light, once a simple phenomenon, has revealed itself to be a cosmic enigma, a key that has unlocked some of the deepest mysteries of the universe. Its dual nature, both wave and particle, challenges our classical intuitions, forcing us to confront the profound strangeness of the quantum realm. As we gaze up at the night sky, we are reminded that the light from distant stars has journeyed for millions, even billions of years to reach our eyes. This ancient light carries with it a whisper of the cosmic dawn, a testament to the enduring power of the universe and the boundless capacity of the human mind to unravel its secrets. But the ultimate question remains, what is light truly? Is it a wave, a particle, or something else entirely, something that transcends our current understanding? The answer, like the universe itself, remains a mystery, beckoning us to explore further, to delve deeper into the heart of existence.